This video covers section 4.6, matrix equations and systems of linear equations. Um, so this section, as you can see, it's pretty short. We only have 4 slides, so I'll try to do it as fast as I can so you can get started with your homework. I know you're dying for that. So what I have here on this first slide is just a series of all the operations and little things that pertain to matrices. And so, for example, if we're adding matrices, they are associative, meaning that you can associate, in this case, A and B, and then add matrix C. Or you could associate first B and C, and then add that to matrix A, and you will get the same thing. And we're talking about addition, that's very important. Addition is commutative. If you add matrix A plus B, is the same as B plus A. The one that is not commutative, and it's very, very important, is matrix multiplication, but addition it is. Then we have the additive identity. For that will be the zero matrix, meaning that if you add any matrix to the zero matrix, you get the same matrix. And the other one will be the additive inverse. And the additive inverse will be negative A. So this is negative A. And the additive identity is the number 0, or the zero matrix, I should say. That is for addition. So when you add a matrix times its additive inverse, you will get 0. Now for multiplication, we have that multiplication is associative. That's fine. You can multiply 2 matrices, B and C, and then multiply that times A. Or you could choose to multiply A and B first, and then multiply that times C. That's okay. The multiplicative identity in this case is what we were talking about. The identity matrix, the one that will look like this with zeros and ones across the main diagonal. This is the main diagonal right here. So that's the identity for a 2 by 2. This will be the identity for a 3 by 3. Okay, and so if you multiply a matrix times its identity, you get the same matrix. Now the multiplicative inverse, that's the one with this notation. It looks like the exponent. And so the idea is that if you multiply a matrix times its multiplicative inverse, you will get identity. And in that case, that one is commutative, only that one. Then we have here combined properties. So that's if you combine addition with subtraction. And so if you say that 2 matrices are equal, as long as you add the same matrix, that equivalence will still remain. If you're saying 2 matrices are equal, if you multiply by the same constant, the equivalence is still there. And that will, of course, work for left or right multiplication, like that, as long as the multiplication is defined. Okay, and I don't know if you ever wonder, but when are we going to get to division? Well, never, because there is no division of matrices. So what we do is we multiply by the inverse. So if you have, for let's say, number 4, and you want to divide by 2, isn't it the same as 4 multiplied by 1/2? Yes, it is the same. So that's what we're going to be using, that same idea, that since there is no division, we will have to rely on the multiplicative inverse in order for us to divide. Now, why is division important? Well, this is actually the last method we're going to look into to solve systems, and it's called with the inverse matrix. So let me give you an example first with, let's use some numbers. And so we have 4x is equal to 16. So to solve this equation, typically, don't write anything, please. You will say, well, we divide by 4, right? So that cancels, and that gives me 4. Yeah, very simple. Or I might tell you, if you have this equation, 4x equals 16, I might tell you take this number 4 across, the 4 is multiplying, so you need to divide. And that's what you do. So in reality, what you're doing is you're just using inverse operations. And so you're doing the following. you know that you need to turn that 4 into a 1. So you're going to use the multiplicative inverse, and you do that to both sides. What's the multiplicative inverse of 4? 1/4. And so we have here 4x. And here we have 60. Now we multiply, so fractions, we have to multiply straight across. So 1 times 4x is 4x. Here we have 4 times 1 is 4. And then here 1 times 16 is 16. 4 times 1 is 4. Then we could say that the 4 divided by 4 is going to be 1. So 16 divided by 4 is 4. And then here, the last thing I need to do is just turn this 4 over 4 into a 1. So 1x is equal to 4. Now, I'm going to do the same, but with matrices. And so we're going to use this idea here. And so I'm going to call A is going to be my coefficient matrix. Then we have matrix B. Actually, let me define them first. So matrix A will be the coefficient. And this will pertain to a system of equations. We'll get to that in a minute. Then we have matrix B, which has the constant terms. And then we will have matrix X, which will contain the variables. So the idea is that we have this with matrices. All these are matrices. And so if we want to solve for the variables, we have to solve for this matrix right here. So you might think, well, let's just divide by A. But remember, I told you there's no division with matrices. So what we need to do is multiply by the inverse of matrix A. And we have to do that same thing on the right side. Now, we saw in the previous section that if you multiply a matrix times its inverse, you will get identity. And so what do you get if you multiply a matrix times the identity? It's like multiplying a number by 1. You get the same number, or in this case, the same matrix. So the big idea here is that to solve a system of equations, it will be found by multiplying the inverse of coefficients times the constants. And it's very simple to do. It's very important to note here that the inverse must be on the left side. We cannot do it this way, so we will always have the inverse on the left side of the constant matrix. And that is because of the dimensions. So remember, the two numbers in the middle have to match. So don't do this and multiply the inverse of the coefficients times the constants. Now let's see how this is done. So we have a system of equations here. And we don't have x, y, z. Instead, we have x sub 1, x sub 2, and x sub 3. So the first thing is to make sure that the system is written in order, meaning you have one column is all x sub 1, the other column is all x sub 2, the other column is all x sub 3. So we construct the coefficient matrix, which is what you see here, matrix A. And so these numbers are coming from the system of equations. So if you look at the coefficients for the first row, we have 1, -1, and +1. That's what we have here. Second row, we have 0, x sub 1, so that's why you see a 0 here. And then we have 2, +2 for x sub 2, and -1 for x sub 3. So we see 2 and -1. Then the third row, we have 2 for x sub 1, +3 for x sub 2, and 0 for x sub 3. So that's why you see the numbers 2, 3, 0. Now, this matrix, X, remember I told you, it's called the variables. This contains the unknown variables, the ones that you want to find. So we're using X of 1, X of 2, and X of 3. Remember, the little subscript has no numerical value, it's just a name. And then here, matrix B is the constant terms. Where will you find the constant terms on the system? Well, those are the numbers that you find on the right side of the equal sign. So in this case, they're all 1, 1, 1. So to solve for the system, what I need to do is use this idea. So I need to multiply the inverse of this matrix times the constants, and that will give me the variables. So this one will be 1, negative 1, 1, 0, 2, negative 1, 2, 3, 0. And of course, when I enter this on the calculator, I'm going to be careful to use this notation. Negative 1. And then times the constant terms, which are 1, 1, 1. And so that will give me the variables x of 1, x of 2, and x of 3. So I'm going to go to my calculator, enter the coefficients matrix, which is a 3 by 3. And that is 1, negative 1, 1, 0, 2, negative 1, 2, 3, and 0. And so remember, we need the inverse of that to find the solution to our system. You must use those little negative, the one below number 3, and then, oh, I'm not out of the exponent, so I have to correct that. I'm going to use the right arrow, and now times, and then I'm going to enter the constant matrix. And that was a 3-row, 1 column, so I need to change that here. 1 column. And those constants were all 1s. That's not going to be the case all the time. And then we press enter. Now keep in mind that you don't enter just the coefficient matrix. You must get the inverse of the coefficient matrix. And we get our answer. So what does that mean? That means that x of 1 is equal to 5, x of 2 is equal to negative 3, and x of 3 is equal to negative 7. So remember, the product we got here is 5, negative 3, and negative 7. On the right side, we still have this, just the names of the variables. And there was another property, that equality property, that said that if the matrices were equal, as long as they have the same address, they're equal. So that means x of 1 is equal to 5, negative 3, and x of 2, and finally, x of 3. Okay, so we're almost done with this section. Just bear with me. So let's go to the next slide. Okay, so we're going to use the same idea. Remember here, and this is how you will find your solution. So let's construct the coefficient matrix first. And so that will be 1, negative 1, and 1. I'm looking at the coefficients of this first row. Then we will have 0, there's no x of 1 there, then 2, negative 1, 2, 3, and 0. And so that times the variables, which are x of 1, x of 2, and x of 3, will equal to the constants, which are 3, 1, and 4. And Those are the constants. So now what do I need to do to find the answer? Well, I'm going to have to use this idea. So the variables, x sub 1, x sub 2, x sub 3, now I'm going to put them on the left side, it's the same thing, will be found by multiplying the inverse times the constants. And so the inverse for this matrix is actually going to be 3. Remember, you could find this on the calculator as well. 3, 3, negative 1, negative 2, negative 2, 1, negative 4, negative 5, and 2. And so if I multiply that, I will end up with the following. X sub 1, x sub 2, x sub 3. And here, I will get the numbers 8, negative 4, and negative 9. And so on this one, if you are confused, remember this matrix is representing the inverse already. This one is just A. This one is already A inverse. So you could also do that on the calculator, or you could do it like we did before, enter the original, get the inverse symbol, and then multiply by the constants. Okay, so problem B, if we solve it the same way, we will be getting the variables x sub 1, x sub 2, and x sub 3 by getting the coefficient matrix. Now in this case, I'm going to write just the coefficients. So 1, negative 1, 1, 0, 2, negative 1, 2, 3, 0. And then make sure that you enter that negative 1 notation. And then you multiply by the constants, which are here, negative 5, 2, and negative 3. And so what we will get is that x sub 1, x sub 2, x sub 3 will be equal to, after multiplying this on the calculator, we will get negative 6, 3, and 4. Okay, so we're done with that step, with that slide. So we have one left, and that is, of course, a word problem. So we have an investment advisor currently has 2 types of investments available for clients. A conservative investment A. So the conservative investment A pays 10% per year and the other one, a higher risk investment, we call it B, and that pays 20% per year. So it pays more, but it's riskier. So clients may divide their investments between the two to achieve any total return desired between 10% and 20%. However, the higher the desired return, the higher the risk. How should each client invest to achieve the indicated return? So first we need to create 2 equations, and the way we're going to do this is by first defining our variables. So we're going to say that x sub 1 is going to represent the amount. The question is asking how should each client invest? So those are going to be amounts of money divided into investment A and investment E. So amount invested in A, the conservative one, and x sub 2 will be the amount invested in the other one, the high risk. And so if we add the two amounts invested, they will add up to this, K sub 1. Now K sub 1 right now is just not a constant, it's just a variable. Then we look at the second equation, and well, first of all, this first equation is talking about the total amount invested in both A and B. Then my second equation is going to talk about the total annual return desired. So remember that this one has a 10% return and investment B has a 20% return. So 10% as a decimal is 0.1 or 0.1 x sub 1 plus the 20%, so that will be 0.2 or 0.2 x sub 2. And that will equal to this, to K sub 2. So this will be the general form that we're going to solve the problem, but we have 3 clients here. 1, 2, 3. So each client is different. So let's see. The first client is investing 20,000, and that first client will like to receive a 2,400 return. So for client 1, we're going to say the following. We're going to say that K so K sub 1 is actually going to be here, 20,000, and K sub 2 will be 2,400. And so we create the system that will look like this. X sub 1 plus X sub 2 is equal to 20,000. Now that's the total invested, only for client 1. We're only talking about client 1, this one. The other one will be the return desired, so 0.1 X sub 1 plus 0.2 X sub 2. And that should be equal to this. That's how much this guy wants. Okay, so now the next step is to create, and this is for client 1, to create the matrices. And so here we're going to need matrix A, not just matrix A for coefficients, but we're going to need the inverse of that. So we are going to need that. Times the constants, and the constants will be 20,000 and 2,400. And so once we do that, we multiply. Of course, make sure you enter inverse on the calculator. Once you get that multiplication, you will get 16,000, and the other one will be 4,000. So what does that mean? Well, it means that client 1, if he wants to get this much, he should invest 16,000. That's what we got for X sub 1. So that means he should invest that in investment A, the low risk, the conservative investment. And he should invest 4,000 in the other one, investment B, the high risk investment. So now let's see what will happen with client 2. So for client 2, we're going to have the same system, but what's going to change is the K1 and K2 these numbers. So this one will be equal to 50,000. That's the total amount invested. And this is the amount desired. This is how much client 2 wants to get back as a return, and that is 7,500 or 7,500. So if we do the same idea. Remember here we're talking about different clients, so we will use the same as the coefficient matrix, but we need the inverse of that, and we multiply that by the constants, which is the total amount that he's investing, he or she, and the total amount of, I'm sorry, that should be at 50,000 from here. And remember, where did I get these numbers from? I just got them from the table, just right here. 50,000, and the other one, he wants to get that much in return, 7,500. And so if we multiply that, this is an equal, sorry. So if we multiply these two matrices on the calculator, we will get 25,000 and 25,000. So actually this one is telling us that the best client 2 could do, if he wants to get that much back, is to split his money in half and half, and then he will get that. Client 3, I'm going to leave that for yourself, but the only thing you should do is replace 50,000 and 7,500 with this numbers, 10,000 and 1,300. And so for client 3, I'm going to give you the answer. Client 3 should invest 7,000 in investment 1 and 3,000 in investment 2. And so if you want to solve it and set up your system, remember, all you will have to replace will be this quantity and this quantity, but the inverse will remain the same. This one is the same thing. You will just have to replace 50,000 with 10,000 and 7,500 with 1,300. And then you should get the numbers that I'm showing you here and here. And so that is the end of the video. Thank you for watching. Don't forget to do your homework.